Today we'll review the final exam, CHEM 1211, and we'll go through as much as we can. And if you have any question, just you know how to contact your instructors if you have any question. Correct? So let's start here. We'll start with the convergence, and as you can see, this is the first problem here. You have the density. Density is a ratio between mass and over the volume. But here it's not just about the value of the density, it's about the convergence between English to metric, metric to English, and vice versa. So here, the density of the helium, just take this one here. Density of the helium is this one here, kilogram per cubic meter. And what is the density in pound per cubic foot? So as I said, density is mass over the volume, and we have the value is 0.164 kilogram per cubic meter. So we need to get first the kilogram, the mass, okay, into pound, and the other one we have to get the meter cube into foot cube. So the whole information given to you is 1 kilogram is 2.2 pound, and 1 meter is 3.28 foot. So let's start. So density is, let's say this is 0.164 kilogram per meter cube. We'll do one at the time, okay? So you can make it tables or make it parentheses. We can make it table here with columns. So I need to get rid of the kilogram and then try to get the pound there. So the kilogram will come here and the pound will come up. I use this to my advantage here. 1 kilogram is 2.20 pound. So this one here, we get the pound here first as a mass, correct? Then next, and we can take it is units out, cancellation. Keep an eye on unit cancellation, kilogram to kilogram out. Oops, sorry. Sometimes it does that. So. Okay, so, and then we have to get the meter, cubic meter into the foot cube. I mean cubic meter to cubic. So here it is. So I will say, where should I put the cube here? What's next? I need to convert the cubic meter. So where I put this one, down or up? What do you think? I will take advantage on this, correct? So this is down here. I have to put one meter here. Take advantage on this is 3.28 foot. However, if you look like this is not the volume. We said the volume area is square. The volume has to be what? Cube. The area all the time square, and the normal length is just without just a plain number like a meter. Meter square, that's area, meter cube, that's the volume. So what I will do here is square the whole thing, correct? So by doing this, now I have all the setup there. So then this one here will come when I cube it. This will come, let me just show you how, I'm showing you how to cube it. Then we'll do the cube here together. So it is, and we'll say this is now, I cube this one here, I cube this one here, I cube this one here. So now this one here, the units cancellation, the cubic meter of the cubic meter out, and here you have all the units. So that's what you need, this with this. Pound is the mass, and the cubic foot is the volume. So you set it up, and then you make all your calculations here. Multiply this by this, divided by this 3.28 to the cube, correct? So doing this, I mean, I'm not going through the calculations, but everybody has it? Everybody has this? What's option we have? What do you think what's option is the correct answer? Everybody has it? So, as I said, we'll not lose our time because we need to cover as much as we can. But this is the setup you have to look into. You are looking for the mass over the volume. The mass has been converted from kilogram into a pound. You have the conversions given to you. And then the volume has to be converted from cubic meter to cubic foot. And the whole thing is given to you. You have to watch. There is the volume in the cubic unit, not in a square, in the cubic, correct? And this is the setup here. And if you have done the setup, somebody has it? Yes. B? She said B. Okay, let's see. The answer is here. Let me refresh this one here and then look at the answer. The answer is A. The answer is A. It's A or B? Yeah, that's so. Let me take this. Everybody has the setup. Let me go here and look at the setup here. Everybody has the setup here. Yeah, that's just a calculation error. Sometimes you have this is a cube. This one here is a cube. This one here. Let me see. Let me show you. This one is a cube. You have to cube this one. This is cube here. Cubic. Yeah. Okay. Yeah. Okay, so I'll take this one out. Let's see the answer. The answer here is the same setup we did. The answer is A. The answer is A. And here it is. The answer is given to you, the same setup we did. Column or parentheses, whatever you like. That's the way it is. And you have to watch for the sig figs. You started with 3 sig figs here. And your answer has to come up to be 3 sig figs as well. Correct? So that's the answer. Answer is A. So now let me take this one out. And now just here is an overlapped question, can be used in the lecture as well as in the lab. So what is the reading now? If we read this one here, how much does it read? So you started all the time, and you have to watch to the scale. And the scale, the subunits. So you have, here's 20, that's your start, and here's your end, 21, correct? So, and then here is, what is this here? 20 point what? 5. And then you have to estimate in between, correct? So what will be your answer? Is 20.5 what? 20.5, and then you have to estimate the meniscus, the bottom of the meniscus here. So 25 point, maybe 20.56, 20.57, correct? Something like this at the bottom. So everybody knows how to read it? Everybody? So you have to look where do you start with, where you end with. This is your limitation. 21 higher value, lower is 20, and then you go, the subunit is 20.5, and then in between you have to estimate. That will be maybe more or less 6 to 7, maybe. Yeah, 6 to 7. So which your choice will be? Which choice? D. So the answer is D. Let's see if we have this one is correct. The answer is D. And let's see, it is. The answer is D, correct. The answer is D. So let's take another question here. If a palladium nanoparticle has a density of this is the density given to you, correct? This is the density here. What is the mass of nanoparticle with a volume of this? So remember, I put for you the formula here. It is very crucial to know that you have a main formula. This I call it main formula, and then you have two sub-formulas coming out of this main. This is the main formula. Main. The one sub-formula is the mass, which will be cross-multiplied, D multiplied by density multiplied by the volume. And the other sub-formula is volume, mass over density. So out of the main, I have two sub-formulas. So now you can, they are asking about the volume, which is this sub-formula here, correct? So they are asking about this sub-formula. So now the volume is mass over the density, correct? So it is, what is the mass? The mass is, what is the mass? They're asking the mass. Well, the mass is here. They're asking about this, not this. So not this here. You take this one out. They're asking about the mass, not the volume. But those are the two sub-formulas from the main formula. So then we'll have this one here. You can. So mass is from density multiplied by volume. The density is 12.0 gram per centimeter cube, correct? And then you have the volume is 1.8410 minus 21 centimeter cube over 1. I did it in column. You can do it in parentheses, either or. The idea is to cancel the centimeter cube to centimeter cube. This is a question, overlapped question between lecture and lab. And remember, that's all the time students they forget. 1 ml is 1 centimeter cube. Keep this one in your mind. We use centimeter cube only for solids. Palladium is an element, solid. That's we use centimeter cube. If you have a liquid, then you have milliliter. Mass over mass in grams per milliliter. If you have a gas, then the unit will be liters. So you have to watch. Students are sometimes forgetting the centimeter cube is equal 1 ml. So, but 1 ml we use it for liquids. The milliliters for liquids, centimeter cube for solids, liters for gases. Okay, guys. So now, what's the answer here? And remember, you have to observe sig fix. This is here 3 sig fix, and this one is 3 sig fix. So our answer has to be, the least is 3. Both of them 3, the least is 3. So our answer has to be 3 sig fix. And you have to watch for the power here. I will not touch this in my calculator. Keep it at the end. I'll do all the calculation, 12 multiplied by 1.84, come up with 3 sig fix, and then see what's happened to the power. Do not attempt to, that's the major error students will come when it comes to entering those powers, especially if they are negative. So keep this one at the end. Don't touch it in the calculator. Just do the multiplication, and then you can use the power at the end. So what's the answer here? A, B, C, D. Which one? A. Any other option? I don't know. I have no calculator. I want to just the setup. The main thing for me, the setup. If you get the setup, then the calculation is easy. How much is it? How much is it? 2.2, 10 to minus 20. That's 24. Yeah, that's correct. That seems to be correct. So let's see. Yeah, yes. No, that's fine. That's fine. I did study in Germany a long time, the 70s. We are not allowed to use a calculator. So you know how we did it? There's no multiple choices at that time, 70s. So this is just rounded to 12. And this is 1/8, this is 2. This is 24. 10 minus 21. So my answer is 24 10 to minus 21. There is none of this like this. So the only thing I can put go to the left, that would be 2.4 10 correct 10 minus 21. I went to the left, so plus 1. This is 10 4 10 minus 20. So without calculator, instead of 2.21, I got 2.4 10 minus 20. Yeah, we were at that time not allowed to use calculator on purpose because they said that makes you dull, you can't think. So yes, correct, correct. That's correct. That's correct. Yes. And remember this with the scientific things, if you go with the decimal to the left, your power exponent will be positive. If you go to the right, it will be negative. I went to the left, 2.4, one digit, 2.4, and then 10 minus 20. Because 1 plus 1 minus 21 is minus 20. So let's see if our calculation is correct. I think it's correct. So, but anyway, so let's see here. The answer is correct. The answer is A. Okay, so let's go forward. This is like critical thinking. It's based on a concept, but it's a critical thinking. You might have to, or not critical, analytical thinking. It's different between critical thinking and analytical. This you are analyzing something here. So it says which microscopic representation best represents the solution. First of all, you have to go and think about what is the solution. The solution is homogeneous or heterogeneous? Yes, that's very crucial because if it's heterogeneous, then you don't speak about the really solution. Homogeneous mixture made of a solute and solvent. Now, you can go further definition. The solute is a small amount, and the solvent in excess, in larger amount, and both they have to have the same polarity, like dissolves like. Because if they are not dissolving, then you have a heterogeneous mixture, and that's violate the definition itself. You will have heterogeneous mixture. So heterogeneous mixture is not a normal solution. Okay, so it can be suspension, it can be colloidal, it can be other than normal solution we know. So we have a solute in small amount, solvent in larger amount. That's the key. One in small amount, this solute here small, and this is big and small. This is big amount. So both of them, those are amount here. So look at this. So look at this, and then you tell me which one represents a solution. This one is a solution. This one is not a solution. Just look at this. We say we have precipitation there. This is called supersaturated solution. Super, you're exceeding the maximum solubility, okay, of the solute inside the solvent. So this one, you just eliminate this one out. Correct? Now, what's the first one with the A? What's wrong with A? What's wrong with A? A and this one here, what's wrong with this and what's wrong with this? This one is one component, and we don't know whether it's a solvent or solute, but we assume that this one will be will be one of them. Like say this is a solute. A solution cannot be stand by itself by one component. You have two components, or sometimes more than two. You can make solution, but the main thing is both solutes or three solutes or whatever, how many solutes, they have to be least amount combined compared with the solvent amount. So this one here is one component by itself. So this is eliminated. So you can all this analytical thinking by elimination. So which one is, and this one here is the same thing. That's a molecule standalone by itself. Are you following me here? So this one is supersaturated. This one is one molecule. And this is just one type of molecule, one molecule. We don't know it's solvent or solute, it does not matter. Correct? But from the picture of the last one, what does it say? We have two molecules, two types of molecules. Are you following me here? We have one type is the blank one. Those seems to be in large amount. How many dots we have? 1, 2, 3, 4, 5, 6. And the other one is 1, 2, 3, 4. That satisfies the definition of a solution. The solute small amount and the solvent larger amount. Can make sense, guys? So we have eliminated three choices quickly, and then we end up with one correct one. So, make sense, guys? What's that? Yes, but they have to tell you which circles representing the solute, which is not given. Does it say? It's not given. But here from this, I can see the blank one. Those are the solvents because they are large in amount. The smaller one, they are least in amount. That's the solute. So, and if you look into this, I'll take it out now. So you get the idea here, and then let's see if we can see it here. The answer is correct. The answer is D. Can you see it? The answer is D. That makes a lot of sense. And the middle is the second one is the B is supersaturated. A and C, those are one standalone by themselves. The blank one, the C is the solvent, and the A is the solute, and there is no second component is there. So let's take, now we have this, which sample has the largest volume? Which sample has the largest volume? So we have aluminum is 2.7 gram per cubic centimeter. As I said, cubic centimeter, the centimeter cube used for the volume, and the centimeter square for the area. So, and then 1 cubic centimeter is 1 ml. ml used for liquids, and cubic centimeter for the solids, and liter for the gases. So which one is the largest one of those here? And the question is, do we have to do some calculations, or we don't have to do some calculations? So it give you the grams, correct? And it's tell you what's the volume. Well, you can do calculations, but you'll waste your lot of time if you do all these calculations. So volume is mass over the density, correct? Volume is mass over the density. So you have the density and you have the mass. So you can calculate for each one of those. This is 1.0 gram multiplied by, that's aluminum. This is the mass here, multiply, or just take it a column here. We can do parentheses or column, whatever you like. So this is 1 gram here for the first one, over 1. And I need to get the rid of the gram. This is aluminum, so I put 2.7 gram per centimeter cube. That's the value here. This one here is 5.0 gram, and the density is 2.7 gram per centimeter cube. This one here is 1.0 gram divided by the density of copper is 9.0 gram centimeter cube, And the last one is 5.0 gram. And this one here, the density is for copper is 9.0 gram per centimeter cube. In all, the grams cancels out, and then you can look. So now you can look with the values. You don't have to do calculations, correct? So which one is has the largest volume? Which one will have the largest volume? Which one you think will have the largest volume? Looking at those numbers. Looking at those numbers. What do you think, guys? Which one? Aluminum? Which one aluminum? We have two aluminums. B, you mean? Just look at this. First, because you have this 9, those 9s here, those will make the value very, very least, correct? Those will make the values very least compared with the 2.7, correct? So now your choice is 2.7 and 2.7, that's less than the 9s. The 9s, the larger is the amount at the bottom, is the smaller the value, correct? So that will eliminate those two the two values. How about the other one? You have 5, you have 2.7. Those aren't common, but here is 5, and here is 1. Which one is larger then? Which one will be the answer? This one? Is it? Okay, so let's see. Everybody agrees how to do it? Did I do any calculation? Did I divide 1 by 2.7 to get the value? No. You can just set it up and then look at the values. And the larger the number at the bottom, that you can eliminate that value. That will be the least. If they ask the least, then you know there will be the reverse approach. So let's see here. If we take this one out and see what the answer is. And the answer is, our answer is correct. Here they have done for you the answer is very kind, very generous. They put the values, but I will not put the. I will not waste my time to do the answer. I mean, a value. I will look at the values and then just compare from observation. Correct? Everybody is following. So let's see the other one. So which pair represent isotopes? So what's isotope? Somebody will tell me. First, we have to define what isotope is. An element found in nature with different modifications. Correct? An element that found due to what? Carbon, for example. We have carbon 12. Carbon, that's the atomic mass of the element. 13 and carbon 14. This is very large. I think 98 something, over 98%. 99, close to 99%. Yes, very, very noisy. Yeah. Thank you. Carbon 13 is about maybe 1%. Carbon 14 close to 0 something, 0.01. 0.1%, something like this, 0, couple zeros, very, very small amount. So that's just an example here. 0, 0, 0, and then here maybe 3 or something %. So I don't know, but this is just a rough. Carbon 12 is our charcoal. That's the most abundant isotope. So why the carbon has 3 types of modification found in nature, 12, 13, 14. And some elements like mercury has 7. Some elements, they have even 8, 9 isotopes in nature, correct? So why is that? Why is this, for example, this is the way you can write isotope. First the element, then a hyphen, and then atomic mass of that element. So I said atomic mass, then what it says, what's inside the atomic mass? So I give you a hint for the answer. Due to the difference, what's atomic mass? Atomic mass is mass of the protons plus mass of the neutrons. Or we call it just in AMU, atomic mass unit. This is number of the protons plus number of neutrons. number of protons does not change, number of the neutrons. So due to those isotopes are found in nature, due to found in nature here, found in nature due to what? Due to different numbers of neutrons. This is the neutron here. Whoops, sorry. The bottom of the neutron is not correct. So the atomic mass of mass number is 1. The atomic charge is 0. So neutron has atomic mass of 1 and charge atomic number is 0. So because of the neutrons is different, so you'll have the isotope, they have the same atomic number. So the protons, correct? The protons here, they don't change. The protons are positive, they don't change. No change. And those are number of atomic number, correct? Atomic number. So, and those are the smallest number at the bottom, in this case here. So look at the combination that they have the same atomic number. That's a must. Don't worry about the masses in the top. The mass, atomic mass in the top, don't worry about it. Because they can differ because of the number of neutrons there, correct? I will look into the ones are equal amount. This is 24, see? And this is 26. This is not an isotope. Are you following me here? 24 and 26, they are not. Isotope, they do have the same number of protons. Correct? The same atomic number. So this one is 5048. This is not an isotope. Right? Like carbon 12, carbon 13, carbon 14, the atomic mass is 6. However, the atomic number is 6. Atomic mass, the first one isotope is the abundant was 12. The second one, least abundant 13. The least over absolute least is 14. But all of them, the carbon is atomic number is 6. Are you following me here? Does not change. So in approaching those type of questions, first you have to tackle the atomic number at the bottom. This number, the smallest number. So this is 50, 48, 24, 26. Those two options are out of our consideration. How about D? Are these isotopes? Yes or no? What do you think? No. They are not equal. So the only left is the 92 and 92. We don't care about atomic mass. It will be different. 235, 238, those are most abundant ones. And you have 234, as a matter of fact. You have 3 uranium isotopes. 234, that's the least, like carbon 14. And then U35. And then you have 238, that's the most. So that's, we care about the 92. 92 is atomic number, has to be equal in both comparison. If you compare those, they have to come the same thing. Any question about this? Any question? Okay, let's take this one out. And let's see if we can get the answer. The answer is correct. The answer is what? It's correct, 92. So that's what we are looking for. It's not changing the atomic number is not changing. So how many neutrons are in carbon 14? We say the atomic number of carbon is 6, correct? But the 14 is what will be? So neutrons, oops, sorry. It is neutrons, not neutrons plus protons, correct? Equal to the atomic mass, correct? Or atomic mass. This equal 14. This one is neutrons we don't know. plus 6 is the number of protons, atomic number. So then you have the neutrons here will be 14 minus 6. This is atomic mass of that isotope, which is the least abundant of carbon isotope, and this is atomic number or number of protons. Make a note that this number of protons equal atomic number equal number of electrons if you have neutral atom. Okay, if you have what? Neutral atom. If you have an isotope that's charged, cation or anion, then the number of the electrons will change as well. So this is neutron. So number of the protons equal number of electrons equal to 6 here, because we have neutral carbon. Now if I tell you something like this, 14 and 6, and you have to say minus 2, and you have to determine all numbers, and this is an isotope, but it has 2 negatives, then the story will change. Story will what? Change. This is number of the protons. Protons is still remaining 6. No change in them. Number of the neutrons will be 14 minus 6. Correct? So 14 minus 6, this is 8. Which we have done this one. 14 minus. The same thing. Here is the same thing. So, and then, but here, in this one here, we are looking at this. The number of electrons is 6, correct? That's to begin with. You have a negative, you are gaining 2 more. So here it has 8 electrons. But here you have 6 protons, 6 electrons, correct? And the neutrons will be 8 to make 6 plus 8, 14. Are you following me here? This is the case if you have a neutral atom isotope. Isotope is neutral, not charged. But if you have a very rare case that you have an ionized isotope that's a negative or positive, then you have, if it's negative, you have to add those extra charges, which is extra negative particles, or you have to subtract if that's positive, correct? So the answer, which is the answer here, guys? The answer? C. The answer is C. Yeah, that's correct. It should be C. So the answer is 8. Okay, guys, here it is. Which is element present by X 5624? Well, the whole idea of periodic table is based on or built on increasing atomic number. Has nothing to do with atomic mass, because we are not certain. You have to know the isotopes, that therefore you get fractional atomic masses. But what's really fixed is number of the protons is not changing. So based on the increasing number of the protons, which is atomic number, then you base all this order arrangement of the elements in periodic table. So which one I can go to? Which one, guys? Which one? So how I can know this is this element here, X, without looking at the periodic table. I mean, if you have experienced the periodic table, sodium is 23, correct? Which will come after sodium? Magnesium, correct? 24. So this one has to be. So since the proton, number of the protons equal atomic number, and that's what I use to pinpoint the element inside the periodic table according to the number of the proton or the atomic number. Atomic number is 24. Okay, atomic number is 24. So 24 is, it is, should be magnesium. Do we have magnesium here? Germanium. 24 atomic number? No. That's atomic mass. Sorry, magnesium has Atomic mass 24. Sorry about this. So that's not correct. Atomic mass of magnesium 24.3. Magnesium atomic mass. Sorry, I'm sorry. Atomic mass of magnesium is 24.3 gram per mole, or AMU. Yes, look at 24. Look at the table 24. What is that? This is atomic number. Atomic number, not atomic mass. I give you atomic mass here. Which one? Chromium. Yeah, that's correct. Yeah, that's correct. So I mixed the magnesium atomic mass with atomic number. So, but atomic mass of magnesium, you can look it up. It's 24.3 gram per mole. So, chromium. So let's see. Okay, so the periodic table is given to you here, and chromium is 24. Yeah, and can you see the magnesium somewhere? Where is magnesium? What's the atomic number of magnesium? Am I correct? It's 24. So I mixed the 24 with the atomic mass AMU, or gram per mole. So that's, I apologize for that. So, but what was that? Yeah, that's fine. But this one I saw 24 at the bottom, so I said maybe, but that's not the case. We are looking at the atomic number, 24 in the top here, and the larger one always will be what? The atomic mass, because you add the neutron to that. Yes. No, that's in the periodic table. But when you write the isotope, they reverse it. They put, make sure that you understand. Atomic number is number of the protons. You add to the number of the neutrons, or mass of the neutrons, the whole thing will be, the mass of neutrons almost identical, a little bit off of the mass of the neutron. So you can see that the atomic masses will almost double. Yeah, will almost double, depending on the isotope itself. So the average weight atomic mass is the mass of all the atomic mass of all the isotope multiplied by their abundance in nature. So yeah, the small amount, that's the proton number. Then when you add the neutron, which is almost identical, very close to the proton mass, so that would be larger amount, correct? So the 24 multiplied by 2, but you don't know how many isotope chromium does it have. So it should be around, what, 48, correct? But it's not 48, it is 51.2. So that's coming because it has more than one isotope in nature. So it has more neutrons abundant. I mean, more neutrons are there in the 2, 3, or 4 modifications of chromium, isotopes of chromium. Yeah, the atomic mass always bigger than the atomic number, because atomic number is the proton mass, it's the proton amount. But then when you add neutron to them, the amount will increase by the double, plus whatever isotopes present inside. But roughly is the double. Roughly is double the amount, because they are almost identical. Mass of the protons, mass of the neutrons, almost. The neutrons is bigger, but they are it's not that big. Yes, you have a question there? Okay. So, yeah, that's, now you tell me which atom has the most neutrons. So here it is, guys. What we said, this one here? Atomic mass, correct? Those are atomic masses, correct? So I need to get a neutron. So I have to get what? I have to get, if I want to get the number of neutrons, I have to get that's the total. Those are total. So this is total of neutrons plus protons, correct? So I need to get, I have the total here, and this one is asked. I have to go to the periodic table and get the atomic number. Oh, sorry. I have to get the atomic number, which is number of the protons. So phosphorus, what's the phosphorus atomic number is? What's the atomic number? Which is number of the protons. Look it up in the periodic table. Atomic number of phosphorus, guys, which is number of the protons. Let's see. Let's go back, and if you don't have the periodic table, let me go back and look with you here the atomic numbers here. Phosphorus, how much is it? 15. 15. Sit there. Here. This is phosphorus here, guys. Phosphorus is 15. So here it is. Phosphorus is 15. This is 32, correct? It came out 32. So 15 and what is the next one? Because I can't see both of them here. Neon, how much? So this is the protons is 15. Number of the protons 15. Sulfur is 16, correct? After? Does it? Yes. Yes, no? Let's pick it up again. Sulfur is 16. Can you see it? Here it is. And then neon, correct? There is cut off here, but let's see if we can get. No, it's not coming. What's that? Ne. That's inert gas. How much? 10. That's correct. And that's 10. And how about chlorine? How many? 17, correct. So those are close to each other. Now, 20 minus 10, because that's the total mass, minus the proton will give you the neutron. 20 minus 10, this is 10 neutrons. 35 minus 17, how many? 15, 8, correct? And 1, 18. Phosphorus, we said this is 15, correct? 15, and then you have 32. 32 minus 15. How much is this one here? Phosphorus. How much does it have? 32. This is 12, 7, 2, and 17, correct? And how about sulfur? 35 minus 16. This is 15. This is 9, 19. So which one is the largest one? You have 19. You have 17. You have 10. Correct? That's 10. You have 18. Which one is the largest one? Which one? D, correct? Sulfur. So sulfur. So atomic mass is given to you, then you have to just look at the atomic number, which is number of the protons, subtract the atomic mass from the protons, you get the value of the neutrons. So let's see here. Everybody got that? Everybody got that, guys? Okay, so let me take this one out. And the answer is, let's see what's the answer here. The answer is D. And here is well done here for you. Give you all the calculations with it. Same calculation with it. So, which ion has 26 electrons? Now here we are dealing with what? Cations. Cations are what? Somebody will tell me? It does not to be metal. We have ammonium cation, correct? But cation, those combination of atoms or one atom or more, that's really what gives away its valence electrons. Donation. They are donors, electron donors. So they are losing electrons. And the number of electrons donated will be equal the charge appears on that atom. Okay, or that element. Are you following me here? So here it is. What ion has 26 electrons? So how in the world I will know what electrons to begin with? Somebody will tell me? We did the periodic table this last question. So what is very important, from where I can get information about the electrons in those metals here. Here we have all 4 metals, correct? So somebody will tell me. I want to be that the review a little bit interactive, so you can think with me, so we can solve it together. I don't want to give you just the answer. I just want you to think about how we can approach this. So what's the best way to approach this? Periodic table, correct? Yes. And what's next? Atomic number. Atomic number is number of the protons equal number of electrons when the atoms are neutral. When the atoms are neutral, correct? Then when you are giving away some of, not you, but the elements, giving away their own valence electrons, they will appear positive depending on how many they are giving away, donating. So, chromium, what's the number of electrons or protons in a neutral one? You have periodic table, guys? So how many chromium? Number of, I will say number of the proton, that's a neutral, equal number of electrons. So here how much is? How much? No, not the atomic mass, atomic number. 24. So, and this one here, how many? Now we are looking at number of the protons or number of electrons in a neutral one. Correct? And then we'll look at the positive charge. Or if we have an element that's negative charge, we can look into that. So how many iron? 26. Perfect. Nickel? Nickel how much? 22. 28. This is a neutral element, correct? And copper, 29. This is the number of the protons and number of electrons. This is 24 here. In a neutral what? In a neutral atom. Now we have to look at whatever the charge is. 2 means it's giving away 2. So 2 electrons are given away or donated. Here. If you look, this is 2, this is 2, this is 2, this is 2. So what will be then? This one here, number of has 26. So 24. This is not negative. This is positive, correct? 24 minus 2. So the first one is 22, because whenever you have positive means the protons inside the nucleus, positive charge are more, because you have lost negative charges, the positive charge will be more, correct? This appear positive. So minus 2, the first one is 22 electrons. How about this one here? 26 minus 2, 24, correct? How about here? 28 minus 2, how much? 26? 29 minus 2, 20 what? 7. Which one has 26? B? C. That's correct. So this is the answer here. This is the answer. How about I tell you that's carbon 4 minus? What is the number of electrons in this carbon 4 minus? What is the atomic number of carbon? We just say it's 6, correct? This number, the neutral one, has 6. But then you have 4 minus. What should I do? What's that? Add 4. Perfect. Thank you. Thank you. Now you are not sleeping on me, so that you are very awake. So the number of electrons here is 10. Are you following me here? So whenever you're negative, you are gaining those negatives. You are overwhelming the protons and charges inside the nucleus. Correct? So just an example of this. So the answer is nickel. That's correct. The same way we did. Very nice. So the answer is well done. So now let's look at this. Bromine has two naturally occurring isotopes. The most abundant isotope is 50.69, is 3579 bromine of mass 79 mu. What is the other isotope? So we have two isotopes, correct? What is the other isotope? Well, first of all, whenever I approach this, I have to go for elimination without calculation first. Then we can do the calculation together. Elimination is, if we have to have isotope, I ask myself, what is the atomic number first from the periodic table? What is the atomic number? That's what the ACS people, they turn to fool the students with the atomic number. So what's the atomic number of bromine? What is it from periodic table? What is it? 35. So this one is an isotope. Now, how many I can eliminate without calculation? That's 36. Okay, that's not bromine. Correct? That's another element after bromine. So 36. So now I'm dealing with, I eliminated two options. I'm dealing with only two, this or this. So the most abundant one is 56.9%, is this one here, of mass of this one here, correct? What is the other isotope? Well, the most abundant one is this one here. So the sum, the average, we can do it this way here, average weight, atomic mass of the isotope is the sum of the isotopes is the natural abundance. This is natural abundance here. Plus atomic mass. And this is, and this is the sum. This is the sum here. Okay, guys? So I have two isotopes. The most abundant one is this. And what is the other isotope? Well, we have two here. You can calculate it. You can look at the the average atomic mass that appears in the periodic table. What is the atomic mass in the periodic table for bromine? 79 point what? 9 what? 04. AMU, or atomic mass unit, or gram per mole. So the first one here is given to you is atomic mass is 78.9183 AMU, atomic mass per unit. I prefer to use gram per mole because then you know that whenever it comes to stoichiometry, we don't use atomic mass unit, we use gram per mole, which is 1 AMU, by the way here, 1 AMU is 1 mole. 1 gram per mole, sorry, 1 gram per mole. 1 gram per mole. So 1 gram per mole is 1 AMU. 1 AMU, atomic mass unit is 1 gram per mole. So this is gram per mole plus what the most abundant one. So we have this one here, this mass here. Oops, sorry. We have this is the mass multiplied by its what? Multiplied by 50.69 over 100. This is the first one. Plus, what is the mass? What is the other isotope? So we don't know what is this one here. If this is 59.69, what's left out of 100? What's left after 100%? How much is it? 49 point what? 31% multiplied by its what? multiplied by its mass. We don't have the mass. We don't know what the mass, the mass of the second isotope, but we can calculate it. So now you can calculate which one. But do we really? So this is the mass of the 100 isotope. The leftover from 100 is this multiplied by atomic mass. We don't know. The average weight is given to you from the periodic table. The average weight. So, which one you think will be 80 or 81? So it's given to you here two options. Look at this one here, guys. It's giving you 80 and 81. That's the atomic mass. Okay, that's the atomic mass, or the mass itself, or the mass itself. That's what we use here, correct? So you can calculate it and calculate for this to get the value there. But can you imagine what's without calculation? What will be is that? So how much is it? It's going up 81 or it's going down to 80? You can calculate the mass here, correct? And then calculate exactly how much is it with all the fraction it has. So can you calculate, or you can just inspect these values and tell me what that really is? What's that? C or D? The answer has to be C or D. Which one? D? Why is D? Why is D? Okay, just plug D to put this one here. Put this one. You said D. Put 81. Put 81 and see if that's close to 79.904. Okay, guys. So look at this. If you said 81, in those type of questions, you don't have to spend your time calculating. You can just inspect the values, correct? So 50 over 69, that's about a half when I do without calculation. 78.9, that's 79. 79 multiplied by half of it, correct? 49, that's 49 without 31. And then that's 80 here over there. That's here 80 for me. I do without calculation. That's what we learn. 80, this is 79, that's half. And then this is 49, this is the mass. So what will be the mass here without calculation? So roughly, it has to be close to the 80, correct? Close to whatever this is really 870, 79. And this one here will be, the whole thing will be what? 79, half of it is, this is 79 multiplied by half plus 49x. This is 80. So you can tell what x will be, correct? So you can calculate how much x roughly count will be. Are you following me here? I show you how to do that without calculation. You don't spend your time to calculate. Just estimate up. This is 9. This is 5 and above is 1. This is 80. This is 79, half of it. This is 50% about 51, that's half. Plus the mass you are looking for multiplied by 49 over 100. 0.4, that's half of this. This is about half if you look at this. 49 over 100, roughly half. So what will be the mass then? Did you calculate that? Did you calculate? Come on, guys. So you don't have to calculate. Just look at the values, estimate, and then you can tell what the x will be. So this is half. 49 over half. This is half will be 250. So say 25. 25x. This is 90. This is 3. 8.5. That's 39. X plus 25x. 80 minus 39 over 25. So it will be what? 80 minus 39 divided by 25 will give you the answer. So just I don't want you to spend some time doing the calculation, but that's the way you set it up. From the periodic table, you get the atomic mass, which is the average weight. The atomic mass in the periodic table, those average weight because they consider all the isotopes present in nature for each element present, correct? That will be given. That's the 79. I took it from the periodic table. And then that's the given to me for the most abundant, which is multiplied by abundance over 100. And then the rest of the 100 is 49.3 over 100. And then the mass, we are looking at the mass, which somebody told me 81. And the answer is, yeah. Yeah, so it has to be what? D, yeah, that's a mistake, yeah. Some of students, correct, yeah. Some students approached me and told me, so the answer is what? D? D, yeah, D. So, however, here we have, if you look at the answer here, please correct this one here. This one here has to be corrected. The answer is, yeah, that's, the answer is this one here. Not this. Not this. And do you know why? That's because this is, the atomic number is not correct. That's not an, the isotopes is changing of neutrons, but they don't change protons, correct? Not changing protons. They change their numbers, the abundance in nature due to the neutron number. So then you look at the whole thing, the answer correct, and the answer has to be here, D. Okay, 81 is D. Okay, guys, so that's D. So correct this one here, and yeah, that, well, I did. Yeah, yesterday, students approached to me. I said yes. Yeah, yeah. He did it, and I told him yes. I'm aware of this, but we'll correct it. So, but that's the that's the. But the same approach we did. You see here, the same calculation we did. See here, the same thing. Any number you see atomic mass inside the periodic table, that's not the atomic single mass. No, that's the average of all the abundant in nature isotope of that element. Are you following me here? That's you have to recognize, because it's very important to recognize. So here it is. Take this one out. Two isotopes of hypothetical theoretical element X exist with abundance of 30. The other one will be 70. The atomic mass of the first 100. The other one is 1. What is the approximate atomic mass of X in atomic units AMU? Well, that's, we did the formula correct. You can do the formula again. We have the idea is they need the approximate atomic mass of X. This one will be the abundance. The first one is 30%, and its mass in the top, that's the atomic mass here, 100 AMU or gram per mole, whatever you like. I like gram per mole. This is the atomic mass, and it's 30%, 3.00 over 100. That's the first one. That's the first isotope. The second isotope is 70% multiplied by 101. So you have 101 gram per mole, correct? Or AMU multiplied by 70, which is 70.00 over 100. You just calculate this setup. I like to give you the setup, and then you can calculate. And as I said, I like estimation. That will save me a lot of time. Correct? That will give me a lot of time saving here. So as you can see here, cancels. This is 30 here. This is almost cancels. That's, I'm doing the German way of in the 70s. Those cancels. You get 70 point whatever, 70 point what? 70 around 70 plus 70. So my answer is closer to 100 something gram per mole or AMU. So which one is? Although we have plenty of those then I have to be very picky because it has 100 this, 100 this, 100 this, 100 this. So I have to be more accurate here. So I cannot do estimation here. I have, because it's 100. We know that's 100, correct? But it's because 101 is more than 100, correct? So, and then 70, so will be more than 70 here. Here will be more than 70. Here is 100, that's correct. 100 cancels 130, but here is more than 70. So if you have 0.7 multiplied by 101 is, what will be 0.7 multiplied by 101? So what's that? What's that? Yes, yes. So which one, yeah, guys, you got? Which one? Come on, guys, which one? See? See? That's right. You see here, this is 70 over 100, that's 0.7 multiplied by 101. So you can, this is 707, and then something like this, correct? That's 70 over 100, that's 0.07. So this is something like this. Yeah, 7. 107. 107. That's, I'm looking for the decimal. So, okay, guys. So you can do this exact calculation with this because it has a decimal there. So can I take this one out? What's that? Do it again. Okay, let's do it again, and then you have the calculator ready. So we have the abundance, the sum of all the abundance multiplied by their atomic masses of each isotope present. You have two isotopes. The first one is 30%. Means this one, this is your 30%. Correct? And its abundance is coming from, that's the atomic mass here. Those are the atomic masses here. So this is 100. So therefore, I can take the hundreds. The hundreds cancels out. That's the first one. That's the first isotope. The second isotope is 70 over 100, correct? 70.00 over 100. Multiplied by 101. This is the 101 here. So this is 30 here. 3.00 AMU, atomic mass unit, or gram per mole. I like gram per mole more because they are identical. 1 AMU, 1 gram per mole. So either or, plus the 100, correct? You have 70 and multiply 70 multiplied by 101 divided by 100. How much is it? How much is it? Two isotopes exist with abundance of 30, and then what is the approximate atomic mass of X? So how much you say? 70.7 AMU or gram per mole. Add those up here together. How much they are? Calculations, correct. Yes. Correct. Correct. 5, correct. Correct. That's correct. So guys, now it's okay? Everything's okay? Yeah. Okay, so let's take this one out. It's 107. The whole thing is given to you here. The same thing we did. Okay, guys. And that's, again, that's another analytical, but this one is much better. This one, why is much better? Because it is giving us the codes, the key. What are those blank ones? What are the darker ones? That's the code there. So the darker ones is isotope 12 of carbon, and the blank one is carbon isotope 13 of carbon. So it said an English sample of carbon contains 20% of 12 and 80% of 13. So 80% natural abundance. By looking, we are expecting more what? More blanks, correct? More blanks and less darker, more blank circles, darker circles. So now you look at this, first of all, elimination. This is one type, correct? And this says we have sample of 20 to 80. So that's like 100% of isotope carbon 13, correct? That's out. And then look at the other one. Well, look at the other one where we have 80 to 20. My intuition can, how about 8 circles to 2 circles? 82, correct? So 80 to 100, 80% to 20% is, take the percentage out, it's like 2 to 8. So let's calculate and see what will happen. I have 2 of those carbon 13. This is 1 and 2. And then I have 1, 2, 3, 4, 5, 6, 7, 8. This is 8. Well, the ratio here is 2 to 8, correct? Which is you have the black one is, this is carbon 13, and this is the darker one is, I mean the blank one is, the darker one is 12, correct? Oops, sorry. It is. So the darker one is 12. I'm looking at the percentage here. This is C12, correct? That's the darker one. Is C13. So that's the percentage here. So here I have 1, 2, 3, 4, 5 of the darker one, or maybe 1, 2, 3, 4, 5 to 5, the C13 to C12. 5 to 5. Well, 5 means 50 to 50, so I can eliminate this easy. Then the only left is for me is A or C, correct? We started to see carbon 13, that's the blank one. The carbon 13, the blank one is here is 8 to 2. This is, the black one is carbon 13 to carbon 12, the darker one. This or this. So we have eliminated both. Not this, sorry. This one we did not eliminate. We eliminate just this. We eliminate B and D. So which one now? So you have the answer there. So you have the answer. What's the answer now? I gave you the answer now. We have 80 of the carbon, 80 blanks. The carbon 13 is the carbon 13 is 80, those are the blank one. The majority is blank. And the other one is the opposite, carbon, this is, you did not even tell me, that's the reverse here. Correct? That's the reverse? That's the reverse. So the black ones here is carbon 12. And the blank ones is carbon 13. So, which is correct? This or the other one? Which is correct? A or C? C, correct? C. So I took the percentage as the number of absolute number of the circles. that's doable because that's a percentage. But if there is a not percentage, then I can't really take this as a ratio. But this is a very good ratio, 20 to 80. This is 2 to 8. So the answer is this one, correct? So again, it's no calculations, no nothing. Just you look at the whole thing here. So here it is. The answer is C, correct? So here it is. Which group contains non-metals, metalloids, and metals? Well, that's I have look at in the periodic table. Which one has all of them? Non-metals, metalloids, and metals. Well, you know that if you go to the left of the periodic table are mostly metals. If you go all the extreme to the right, that's non-metals. However, in between, there's some groups. They do have mixed. Some of them non-metals, and some of them metalloids, and some of them 3 of those at once. Which one you think that will be the case? And number those characteristics number, that's the modern periodic table numbering, correct? Minus 10, you'll get the idea. So you go from 13 when you go 3. So 13 is minus 10. This is 3A. 15 minus 10, that's 5A. 18 minus 10, this is 8A. I like the old, and I use old and the new one. The old will give you the valence electron distribution. A and P will give you the A is the main group, and the B is transition element group. That will give you that's the old one, A, B, and this is minus 13. You get the idea. So this one A, let's forget about this. This has just absolute metal. 18, 8A, that's absolutely forget about those two. Eliminate those two. Why? Absolutely metals, absolutely non-metals. 18 is 8A, absolutely that's inert gases. Has all of them gases here, and this all of them metals. Now you are dealing with, you eliminate. Always elimination is very good because that will reduce the time in looking at the problem. So look at the 3A or 13, or look at the 15 or 5A. Which one has of those groups all those 3? So which one? Which one, guys? You have the periodic table, correct? So the 3A has started with boron, correct? And then after that, boron non-metal. Then start, or metalloid, then start to be what? Metals will come in, correct? Aluminum after that, as I remember. So now the 15 start with, I think is 5A, start with nitrogen, correct? Then phosphorus at the end. So then we'll start the metalloid, and then they start at the bottom of them, you have metals, correct? Heavy metals. So let's look at the periodic table. It is, so between 3A and 5A, or 13 and 15. So here it is. Let me take this one out. So now 13, you have the boron, that's a metalloid, correct? And then you have, if you look at the whole thing here, so between 13 and 15. So let's look at this here. Between this and this, you will see here, all those are, except for this, metalloids, all those are metals. However, 15, then you start have the non-metal here, non-metal here. Now the metalloids will kick in, and then you have metal, heavy metal bismuth. Okay, and then the new one here, the 115, that's just a metal one. So the 15 has all 3 ones. Started with non-metal, then go to metalloids. Remember the metalloids are the stairs. You can see those stairs here and whatever. So this stair here. So those are the metalloids here. About 7, I think, 7 of them. So can you see that? So the answer is 15, and that's C. The answer is 15. The 13 or 3A has one metalloid, boron, but then all of the rest are metals. All the rest from aluminum down, all the way down, those are metals. Correct? Those are metals. The 15, that's the one has both. And as a matter of fact, 16, oxygen, sulfur, then the selenium here, those are non-metals. Then you get to the Te, tellurium here, that's a metalloid. Then you go plutonium, correct? That's a metal. 116 a metal. So 15 and 16 are the only one, the two only groups they have, all those three. The rest are absolute. So 8A, this you can't see it there. They have all inert gases, 8A or 18. So you can look into that. So both of them. So here it is. Okay. Redundant. Some of them redundant. Yeah. I agree. Yeah, the same thing. Okay. We'll take one of this one here. Yeah, that's because they are redundant. Some of them redundant. I agree. Yeah, my students they have it already. The old one. So let's go for the naming. What's the name of this compound here? Naming compound, quick. What's the name of this compound? First of all, is this ionic or covalent compound? What's this compound is, guys? Look at all the options you have. Well, you have titanium and phosphorus. The phosphate. The phosphorus is 3 minus. That's titanium we don't know, correct? When you combine to them, the 3 will come, just the value, not the, will come underneath. So you have Ti will be 3, and the phosphate will take over whatever from the element of the metal here, correct? And we have here 4. So this one has to be what? 4, correct? This one has to be 4 plus. So it will be 4. So this is titanium, what? What's the number of the charge here? Titanium 4, correct? So which one then is a phosphate? Which one is from those? Which one? This is 4, yeah? Titanium 4, correct. So let's go further here. That's just an ionic compound. We'll go further here. Those naming, you can look into them. Yeah, this we took ionic, we'll take non-ionic, which is covalent. What's the name of this compound? Quick. Dinitrogen pentoxide. That's correct. So this is correct. Dinitrogen pentoxide. And the answer is this one here. So let's go further. Now, okay. A single molecule of certain compound has a mass of this value. This is the mass. Which value comes closest to the mass of mole of this compound? So it has a mass of this, correct? And you need to get the closest mass of this compound. So a molecule. Guys, that's what I tell my students. Always, what's the key point? Who's my class? Who's my class? I have 2 students here in my class. What I said, my class, the review we did. Anytime I have the keyword molecule, atoms, formula units, or sometimes they call it ions. What it means? Somebody will tell me, my students, what we have to use. Avogadros, yes, Avogadros, that's what I said. And this is a keyword. That's an answer indirect to answer this question. Anytime I have a molecule there as a word, or atoms, or formula units, or sometimes I use ions, then I'm dealing with Avogadro's number, regardless. So that's the keyword. So you have the masses here, correct? So it has a mass. What value comes closest to the mass of 1 mole of this compound? So you need the moles of this compound. So I put the answer here. Sorry. Why wait? What I did? So I put the answers there, but it's already the answer circled. I did not realize that's the answers. I'm sorry. But yeah, that's the answer is D. Well, how will you do it? Because the keyword is atom, molecules, ions. You have to use Avogadro's number, which is gram. You have the 1 molecule here, so 1 mole. 1 mole is, guys, Avogadro's number of atoms, Avogadro's number of molecules, Avogadro's number of formula units. Or some textbook, they put sometimes ions. However, the 1 mole is a ratio between mass over molar mass. So you have 4 definition of a mole. 4 definition. 4. This is one here. Mass over molar mass. This is the second definition. This is the third definition. This is the fourth definition. Correct? So a mole is mass over molar mass, a ratio, and is equal to Avogadro's number of atoms or Avogadro's number of molecules of formula units. So you have 1 molecule has this amount of grams. Correct? So you have the grams here. That's what they did. Grams here, 3.4, 10 minus 22 grams in 1 molecule. Correct? Then you have multiply Avogadro's number of molecules. Correct? Oops. Avogadro's number of molecules. Where is it? Here it is. Is it here? Yeah. Avogadro's number of molecules per mole. Per mole. Per mole. Per mole. So the molecule here is the top is molecules, by the way. It's not molecules here. This is molecules here. And the molecules will cancel out with, it's unfortunate here. Molecules will cancel out with the molecules here. Molecules will cancel out molecules. Does not want to take at the edge. So molecules will cancel out with the molecules. You have gram per mole, which is the atomic. This is gram per mole, which is defined as a definition of a mole. A mole is a ratio between mass and molar mass. Gram per mole, that's not atomic. That's atomic mass. If that's one compound, if one compound, that will be molar mass. Correct? So that will be molar mass. Okay, guys. So let me take this one out. Answer is D. So let me I need something in chemical equation. Just so what's that? This one's redundant. Oh, okay, this one, yeah. Well, what's the mass of gram of oxygen does 25 grams of aluminum carbonate contain. And it's giving you the molar mass, correct? What's the definition of the molar mass? Well, we have two definitions of the molar mass, correct? Two definitions, molar mass. So the molar mass, because we have the mole here, mass over molar mass. That's the first definition. So out of this main formula, I can get sub-formula called molar mass is equal to what? Somebody will tell me? Mass over moles, correct? Mass over mole. This is one formula. The second is the molar mass is the sum of all atomic masses of elements involved in this compound. Okay, so molar mass equal to the sum of all atomic masses of elements involved inside this compound. Involved in the compound. So two definitions of molar mass. So we can get the molar mass either or, whether the top one or the bottom one. Either or. So it's given to us the grams of aluminum carbonate. So the mass is given to us, which is 25.5 grams. And the molar mass is, and remember, this is very tricky. Molar mass is 23.99 gram per mole. This is very tricky. This is molar mass of the whole compound, of whole molecule or compound. But if you look at the question, that's what we had yesterday, remember? In our review with my students, I said, you have to read the question very carefully. They don't ask you, when we did the, I think, empirical formula or something like that, they ask you about one element within the molecule. They ask you about oxygen, which is how many of them there? We have 9 oxygen atoms, correct? In one molecule of the whole compound. Al2CO3, parentheses 3, we have 9 oxygen. So you have to watch for this. Does not ask, because the students will come, will miss the word oxygen and they think they ask for the whole molecule. No, they ask specific. They can ask about aluminum. They can ask about carbon. They can ask about oxygen. Those three elements are making up the what they call it, the whole compound or the whole molecule. So what's the mass of oxygen? It does 25 grams of aluminum carbonate contain. So that's the molar mass. So you start whatever is given to you. What's given to you here? Can I take this one out? Just show you here just the background. I'll take this one out and then we'll do step by step. Always given whatever is given to you. It is. Can I take this one out? So I have here, I start whatever is given to me. This is 25.5 gram, correct, of aluminum carbonate, AlC. That's the whole molecule, over 1. That's given to me, okay? That's the first thing is given to me here. Then I have to look at what's next. I'm looking for oxygen. I'm looking at the 9, I will say 9, I can rate the ratio is 9 atoms of oxygen to 1 molecule of the whole aluminum carbonate. Or I can say 9 moles of oxygen to 1 mole of the whole molecule, correct? So whether you transfer it as an atom to molecule or moles to moles of the whole molecule, atoms to the whole molecule or moles of the whole molecule, either or. So what's next will be, I have to get rid of the grams of the whole molecule. So it will be gram of ALC, because I have to cancel those grams with the grams out. What should I use? What should I use to get rid of the gram? I have here something is given to me. 233.99 gram per mole of ALC, aluminum carbonate, correct? So now the gram cancels out. I have a mole here, correct? 1 mole of ALC of the whole molecule has how many moles of, what is the mass of oxygen? How many moles I have? I have 9 moles. 1 mole of the whole thing have 1 mole, 9 moles of oxygen. So that's 1 mole of the whole compound. So the mole of the whole compound, the mole of compound cancels out. Now I need what? I need, that's 9. I need what? The mass. Well, then I have, what's the atomic mass of oxygen? What's the atomic mass? 15.9999, 16.0 gram oxygen per 16, where are we at? I don't know, 16 gram per mole of oxygen. So if you look at the whole thing, mole of oxygen cancels all, you get only the unit is 16 grams. So you have the 2.5 divided by the molar mass of the whole molecule, and then multiplied by 9, multiplied by 16, you get the grams. You want me to do it again? Let me do it again for you here, maybe. Yeah, this is another ratio, but I did for you the ratio that makes connection. So I did for you the connection. Yeah, you can make a ratio, or you can make the same thing we did. We did this one here. We came out to be 25.5. That's the whole molecule over 1. Then we did, okay, this is the whole molecule here is 233.9. This is gram of the whole molecule per mole of the whole molecule, correct? And then you have 1 molecule, 1 mole of the whole molecule here, ALC. Now, until now, we did not introduce the oxygen. 1 mole of this has 9 moles of oxygen. Now, the atomic mass of oxygen is 16 gram of oxygen per mole of oxygen. And you can see how nice the units are canceling themselves out. So gram ALC with the gram ALC, mole of ALC, the whole compound, mole AC, mole oxygen with mole oxygen. The only thing left is your oxygen. I did it differently, correct? Did I? I did it a little bit. Is this one here? Yeah, so I did it a little bit differently, but I think the answer will be identical. Okay, guys? Well, I think you're right. I have to rest. Our professor here will come and take over, and just keep the recording. Yeah, I'll show you how the whole thing is working. Yeah. No, that's a very simple one. Here it is. We are going to. No, that's I bought from. So you can use it. So what you will do? No, I will wait until everybody is done. So here it is. This is wiping out the whole thing. Yeah, that's wipe out the whole thing here. Yes, the mouse. And this one here, if you go from writing to if you are writing now, for example, with this pen here, so then you cannot go to this. You go to the second one, it will not go. So you have to go to freeze, freeze this software, and then you go the next one, and then this one, whatever is wiped out. Wipe, freeze, and then you go to whatever that is. Now, Okay, she will take over, and then we have the recording here, and we'll cover as much as we want. So I'll leave everything.
I like this. I think I need to apply my.
Well, I use it now.
Yeah,
Always,
right.
We can
Right.
go at the review.
Okay, so let's see how this. Okay, we have empirical formulas. So for the ones of you who don't know me, I am Dr. Vanegas. I teach here at Clarkston. I mostly teach 12-12, but I teach 12-11 as well, 12-11-51 as well. So who remembers how to do empirical formulas? So basically, and let me see if I got this right. I go here, I pick it, and then you can write with this, right? Which is kind of cool. So we have a compound that contains carbon, hydrogen, and oxygen, right? And basically, finding the empirical formula means finding the smallest whole number ratio. So X, Y, Z. Oops, that's a Y. And Z. And what are these X, Y, and Z's? Are basically the atom-to-atom ratio if you're dealing with one molecule, right? Or they are the mole-to-mole ratios if you're dealing with 1 mole of substance. So if I know that my compound is 51.56% carbon and 14.09 hydrogen by mass, how do I go about finding these values? Does anybody remember at all how do we start here? So in those X, Y, and Z are moles, right? Basically, they're finding to the smallest whole number mole ratio between these carbon, hydrogen, and oxygen. So what I tell my students is the first thing you do, how do you find mole? You find the moles doing grams, right? Mass divided by the molar mass. That's how you find moles. So what we need to do is convert those percentages into grams values. And the easiest way of doing that is assuming a 100 gram sample. If you have 100 grams of this compound, it's easy to apply these percentages directly, right? In 100 grams, we know that we are going to have 51.56 grams of carbon, and we are going to have 14.09 grams of hydrogen. And how much is the oxygen? The difference, which is 34.35. That's what my notes say. So I have 34.35 grams of oxygen. So this is in a 100 gram sample. Now you can do 200, you can do 1 kilogram, it doesn't matter as long as you keep these proportions, right? Because the percentages are the same. So now how do I go from grams to moles? Divide by the molar mass of each, right? Or times 1 over the molar mass. So what's the molar mass of carbon from the periodic table? Roughly 12, right? So 1 mole, 12 grams. You can tell I'm not quite as proficient as writing with this as Dr. Ateya was. But please bear with me. This is the times. So then times 1 mole over, what is hydrogen? 1 gram per mole. Sorry. I'm thinking. Wait. Oh no, you have to do with this. Bear with me. How do you erase one thing? Thinner? Oh, okay. Oh, I see. I need to do thick, and it will. There you go. Okay, let me do it better. So each one. Okay. Thinner. Yeah, I know. I'm so sorry. I'm so sorry. I'm getting there. Okay, so it's 1, and now it's, this one. Okay. We'll eventually get this, guys. I apologize. It will take me a sec. There you go. Okay, so I have 1 mole and 12 grams. And then in here I have 1 mole and 1 gram. And for oxygen, each 1 mole contains 16 grams, right? So I'm doing these calculations, and tell me what you get. So 51.56 divided by 12. What did you get? Basically 4.296666, right? So 4.296666. And this kind of calculations is one of those that you sort of forget about significant figures. You want to keep lots of digits because the ratio is what matters. So we're going to round to a whole number at the very end. And then in here, we don't really need to do much because it's just divided by 1. So this remains, and this is moles, right? And this remains 14.09 moles. Of course, if you use the actual mass that is from the periodic table, you get a slightly different number, but it should be good enough. And then we have 34.35 divided by 16, and that gives us 2.146875 mole. That's all my calculator gave me. So now these moles that we got are already kind of like the mole ratios, but not really the ratios, because these numbers cannot be used as subscripts in a formula, right? You've never seen a formula written with the subscript of like 2.146, blah, 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 right? So how do we get to whole numbers here? Anybody remembers from your lecture class? You know this. You know this. How do I reduce these numbers to the small whole number ratio? Forget chemistry, like think math. Do I have any takers? You're tired. We need a break. Everybody up. 5 jumping jacks. Reoxygenate the brain. How do I get one of these numbers at least to be 1? Divide by the smallest, yes. Okay, so I'm taking all of these numbers. I look at them. The smallest is this 2.14, etc., right? So I'm dividing all of them by the smallest, and that will give me like the ratio, basically, or the 1 to something else ratio. So let's all divide all of these numbers. So divide by the smallest. So I don't have any more space in here, but if I divide everything by this, which is the smallest, this becomes 1, right? It looks like this 4.296 divided by this will roughly give 2, right? And let's see what that 14.09 divided by 2.1468875. Ooh, this gives roughly 6.5. So I told you to forget about significant figures, right? But we don't round to whole number necessarily at this spot. I kind of did because I thought we were good. This is a 1, this is a 2. When you divide by the smallest amount in moles, you don't get very close to a whole number. Like in this case, I got the 6.56, which is very close to 6.5. That's a little bit too much rounding. So it's basically half an atom we're talking about in here. So if at this point you get to a like 6.5 kind of number, or like any 0.5 kind of number, what can you do to make these whole? What do you do? Go up and you multiply all of these numbers by an integer that will get you to whole numbers. So what would be that integer in this case? Well, I just need to make this a whole number. How do I make that into a whole number? Well, you don't round up. You don't want to round up because these are mole ratios or atom to atom ratios. So if you get something very close to 1, 2, or to a whole number, yes, you can round. But if you get to like a 0.5, that's literally half a number, half an atom you're dealing with and you're talking about. So you can't round that much. That's too much rounding. So in here, we are getting 6.5. How do we keep this ratio, 1 to 2 to 6.5? How do we keep this ratio, but we make them into whole number? Basically, what we found so far is, and let me see if I can do this. Let's do this and erase these. What we have found so far is 2 for carbon, 6.5 for hydrogen. Dude, this is not pretty. And for oxygen, we found 1. Have you ever seen a formula that has a 6.5 as a subscript? Let me rewrite it. So this is the ratio these elements are present in this compound, the mole-to-mole or atom-to-atom ratio. But have you ever seen a formula with like 6.5 or 1.5? No. So how do I keep the same ratio but make it whole numbers? Multiply by the smallest whole number that gets you to the whole number ratio. And that's exactly it. So what would that be? If it's a 0.5, how do you, sorry. I need to make 6.5 into a whole number without points. Yeah, so we divided all of these values in moles by the smallest amount of moles to normalize it. In essence, we believe we make this one, right? So we make this our measure. And we got about 2, about 1 obviously, and this was the 6.5. It's too much rounding because this is basically 6.5 atoms. If I were to think about one molecule of this compound, it would have 2 atoms of carbon, 6.5 atoms of hydrogen, and 1 atom of oxygen. So you can't make 6.5 atoms, right, in a compound. So how do I keep this ratio, 2 to 6.5 to 1, that have whole numbers? I multiply everything by 2, exactly the answer I was looking for. So basically, if instead of having 2, 6.5, and 1, I make this, I multiply everything by 2, so that now this becomes 13, this becomes 4, and this becomes 2, I have this one, right? So I kept the same ratio, the same proportions, but now I have whole numbers. Does it make sense to everybody? And this happens. You will find 0.5 sometimes. Occasionally, you might end up at 0.33, 0.34, which would be your multiply by 3, all of the values that you get. But most likely it's going to be the 0.5 or 0.3. And sometimes you get even more complex cases, but most of the times. Bottom line is, you don't round the amount in moles that you get. You divide by the smallest amount in moles to normalize it to that value. And at that point, you want to round if you can. So when you round the normalized amount of moles, you want to make sure that you're not rounding too much. Because if you're getting in a 0.5 situation, that's happening too much rounding. You want to keep them and multiply by the smallest whole number to make the same ratio, the same proportion in whole number, which is what goes into your formula. Any other questions? So does it make sense? All good? Okay. And let's see if we're right. I have to go back in here. Yes, I'm getting it. Oh, and wipe. Yeah. So we got it right. Okay. let's see what we have next. We want to count, so the number of atoms in 9 grams of aluminum is the same as the number of atoms in, okay, how do we go about this? How many atoms do we have in 9 grams of aluminum? Compare that to the atoms in, we have magnesium, so all the options below are magnesiums. We want to compare that to 8.1 grams of magnesium, 9 grams of magnesium, 12.1, and 18 grams of magnesium. So there is a hard way of doing this, and there's an easier way to do this. And as you've noticed, a lot of these questions from the ACS study guide, oftentimes, you can do the calculations by all means, that always works, right? But sometimes calculations might make you waste time, and this exam is an intense exam. So what you want to have is sometimes you might want to try to find a way to kind of, cut a little shortcut if you can. If your brain is used to it, you will be able to. So that's why we're doing these review sessions. So how can we go about this? So the long way would be what? What would be the long way of doing this? Well, we need to compare atoms. So we find atoms, right? So we take the 9 grams of aluminum, we divide by the molar mass to find the moles, and we multiply by the Avogadro number to find the atoms of aluminum. We do that for the 9 grams of aluminum and for A, B, C, and D, and then we compare, right? So the other option is to just write down the formula. So if I want to find number number of atoms, so we would do mass, right, times 1 over the molar mass, and then times the Avogadro number, and this is 1 mole, 1 mole. Now, there's also the fact that the number of moles are going to be proportional to the number of atoms, right? So you don't really need to calculate and to involve the Avogadro number, which calculates the atoms. You can just stop at the moles and compare moles to simplify your calculations. So if I want to compare these, let's say that I'm doing 9 grams of aluminum. Let's take a look at where aluminum is and where magnesium is so that we compare the molar masses, because maybe we can even do this without doing any math at all. Once we have the setup, we understand proportionalities between these. So the molar mass of aluminum from the periodic table is roughly 27, right? Yes, grams per mole. And for magnesium, the molar mass is 24-ish, right? 24.3 grams per mole. So if I want to calculate the number of atoms or even just the moles of aluminum, I'm going to do 9 grams of aluminum times 1 mole over 27 grams. See what that gives me. And I can do that and compare that to A, B, C, and D. Do all the calculations. Now, how would I set up the calculation for magnesium? I am going to use B because it's the same grams, so that it gives me an idea of what to expect. So if I am doing it for B, I get 9 grams of magnesium times 1 mole, 4.3 grams. We can do the calculations, or we can even just look at these numbers and which one of these is going to have A, Y, right. Okay, so we're noticing that the molar mass of aluminum is bigger than the molar mass of magnesium, right? So without even doing these calculations, and we're going for moles here, which is the same as going for molecules, or for atoms in this case, because moles is proportional to atoms number, right? It's just a proportionality, which is the Avogadro's number. So because I can tell that the molar masses are different and the molar mass of magnesium is smaller, clearly the 9 grams of magnesium will have more moles and more atoms than the 9 grams of aluminum. Everybody with me so far? So all the other options, so 9 I'm eliminating because clearly it's not the same, right? It's more. And because of the same reason, I can also eliminate the 12 and the D, right, and the 18, because all of these are more grams of magnesium, which will turn into even more moles and more atoms of magnesium. So the only option available in here is that 8.1 grams. So you see how this question, just like some of the older ones that we saw today, you can, kill yourself with calculations. You can just try to use your reasoning, and it will take you significantly less time than, going through all the calculations. And this exam, as we mentioned before, it's an intense exam. It's 70 questions in, about 2 hours. You kind of want to move quickly. And you don't want to spend, 10 minutes on a question. So if there are questions that you can solve just deductively without having to go through all the calculations, which, by the way, every time you get to a calculator, you set yourself up for some mistakes. You kind of want to move quickly and do your best and never leave one question unanswered. So it's in your interest to answer them all. Any questions? Does this make sense? Or we did? Excellent. Now we are erasing this. And moving on. So this is the here. Okay. So this was the answer. And as I said before, if you don't have these slides, you can leave me your email afterwards and I can email them to you. Okay, let's see what we have next. The same is redundant. We've used the Avogadro number before, so I think I'm going to skip it. This also seems relatively easy. Just very quickly, how would you go about this? 6 moles of calcium hydroxide. We are looking for moles of hydrogen. This should be a pretty quick one. Oops. Just by looking at it, this should take you like 10 seconds to answer. You're looking for moles of hydrogen and 6 moles of calcium hydroxide. How many hydrogen atoms are there in each unit of calcium hydroxide? That's the ratio. 12, exactly 12, right? So questions like this, try to pick and choose the battles that you want to pick, right? If it's a question that you think you are going to get right, even if it requires some calculations, go for it. Questions like this, you should be able to see pretty quickly. Each one unit of these has 2 hydrogen atoms, so there is a ×2 conversion factor here. And that's exactly what this is, 12. Let's see, I wanted to get to some stoichiometry because you want to do stoichiometry, right? Let's see if I can get to some stoichiometry. Mass percent, we had any mass percent. Maybe we can do this mass percent. What is the mass percent of oxygen in iron? Which iron is that? Iron 3 or iron 2? Is it iron 2? Oops, shoot. That's actually iron 3. Because it's Fe2SO4 3 times. Sulfate has a charge of -2. So you have a total of, so each sulfate is -2, so the total minus charges are -6 here, which means that in here you need to have +6. Wow. Which means each iron has to be +3. But that's not the question. This was just incidentally, since I had to call it something. So what is the mass percent of oxygen in iron 3 sulfate? So we skipped some of the questions that were naming. I figured it was worthwhile. How do we do this? What's the mass percent of oxygen? So best way of solving mass percent questions is go by the molar mass and figure out how many grams of that element there would be in 1 molar mass of that compound. So we would want to add up 2 irons. How many sulfurs? 3. And how many oxygens? 12. So we have 2 iron plus 3 sulfurs and 12 oxygens. So iron is 55.85, 55.85 grams per mole. Sulfur is 32 grams per mole. And oxygen is 16. Erasing this. 16 grams per mole. So let's multiply each by how many we have. So we'll have the amount in grams per mole in each 1 mole of this compound for each of the elements. So if I do 55.85 times 2, that's 111.7 grams in each mole. If I do 32 times 2, that's 64 grams per mole. And 16 times 12, that's 192 grams per mole. So with these numbers, I can add these up. So 192 plus 64 plus 111.7. So the molar mass of 1 unit of iron 3 sulfate is 367.7 grams for each mole. Did I get the numbers right or wrong? Which slide is this? 64. I think I added up something wrong. Yes, but I got the molar mass wrong. Wait a second. 192 plus. Yes. Oh, because it's times 3. Darn it. I multiply by 2. Thank you. That's what I was missing. Okay. Yes. Wait, let me erase this one too. So 32 times 3, that's 96. And so now we can add them up. Hopefully this will be the right one. Plus 96 plus 192. Yes. So it's 399.6. So this is 1 mole, right? In each 399.6 grams of this compound, how many of these grams are oxygen? 192. So I'm going to do 192 grams of oxygen in each 399.7 grams of the compound, 2SO4 times 100. So that's the percentage by mass, right? And that should come down. It looks like it's about half. So it should be 48. And this is, again, one of the situations that if you have all your numbers and you look at the options, you can tell that it's almost 50-50, right? Basically, this 192 is almost 50% of this 400. So you don't really have to, once you have it set up and you have all of the masses and the molar mass of the compound, you don't really need to do the calculation and waste time in your calculator or risking to make a mistake. You can tell it's none of these, it has to be, right? Okay. Sorry about the molar mass. Wrong. I really want to get to some. Let me see where the balancing begins. Because we have only about half an hour left. So maybe we can do a balancing equation question. Let me see if I can find a good one. 70. Or even, so let's do a dilution since we're starting with solutions here. Okay. Okay, so let's look at this one. We start with solutions and then we'll start talking about it. So what solution volume is needed to prepare a 1.1 molar solution of magnesium sulfate using 10.3 grams of the compound? The molar mass, they are kind enough and they even give it to us so we don't make mistakes calculating it. So what is that big M symbol for? Molarity. So the symbol molarity, what's the formula for molarity? So it's moles of solute divided by liters of solution, right? So we need to find what? So it's in short, is molarity is moles divided by volume. What is the question asking for? The volume. So what is the, how do we find the volume? Moles of solute. Yes, I'm sorry. My proficiency at writing with this pen is not very good. I guess you have to really press it. Moles of solute divided by liters of solution. So what solution volume is needed to prepare 1.10 molar solution of magnesium sulfate using 10.3 grams of the compound? So you're going to find the volume, right? So volume is equal to, from this formula, moles. How do I solve for volume? I can bring the volume up and the molar down, right? Molarity down. So moles divided by molarity. How are we doing with the inverse formulas and rearranging formulas? Everybody knows how to go from here to here, yes? Okay. So I know the formula for finding the volume. I have the molarity. I need the moles of solute. How do I find the moles of solute from what they give me? How do I find moles in general? So if I have the mass of a compound, how do I find how many moles that is? Time. So the it's usually mass, right? So that's our starting point. How do I use the molar mass? And I can make it a table, right? Or I can multiply by conversion factors. How do I use what does this mean? This means that each 1 mole of that compound is 120.366 grams, right? So how do I use that equality in a conversion factor to get me moles, which is what I need from grams? I need to put the unit I want to get to on top, and the other unit I need to be able to cancel it, correct? So it would be 1 mole over 120.366 grams. So the unit cancels. So this will give us moles, and then we take this number and we divide by the molarity which was given. So basically, let's see what that number ends up being. So we have 10.3 divided by 120.366. So this gives me 8.08557. This is moles. This is what you get from here. And you can round it or not. You very likely will get to an answer very close to that. And then we divide that by the molarity, which is given 0.110. And the unit is moles per liter. So it would be moles per liter. So moles and moles cancels. Liter is under once and under twice. So basically we end up with liters on top here. Let me know what you get. We should get B, so 0.778 something, right? Okay. Yeah. I know we are all tired. Do we need a mini break, like bio break to the bathroom, or like a little shaking? Real good. I feel like the energy level is kind of low, so maybe we do need a break. Shake your legs a little. Take a walk around the room. I know it's a long, it's a long session, so I forgot to break it before when we should have given them a break in between us. Oh, okay. All right, thank you. Okay. This. I still have a little smidge here, but oh, that's what I did. Wait, where is that? Okay, so let me get to some, yes. I'm getting there. I wanted to have some balancing equations and then get into some stoichiometry because we are at the end of this. I don't want to keep you here until 1. We need to have some lunch, right? So let's do one balancing and then we'll move to some stoichiometry problems here, which tend to be hard, right? So how are we doing with balancing? Do we remember how to balance and what balancing means and why we need to balance? So balancing an equation is a result of the law of conservation of mass, right? You can't have a runaway element or molecule or anything. You need to have everybody accounted for. And the little problem with this is that, so we need to have correct formula of both reactants and products. So you can't go around changing the substrate, right? You do that by changing the coefficients. And sometimes in going back and forth between reactants and products, you fix something and you mess something else up. But if you proceed methodically and you continue to, check in the reactants and products and check for all the atoms, you should get to the right answers. So, in here, how would we go about this? We have methane plus oxygen that gives CO2 plus water. This is the combustion of methane. So how do we start? I see I have one carbon and one carbon. So carbon seems to be all right, right? And then I move on to the hydrogen, and I have 4 hydrogens and only 2 on this side. I'm leaving oxygen last, not only because it's last in here, but also because I see that oxygen is present in both of the products molecules here, so it's going to be harder to wrap up, and I'd like to wrap up with it. So if I see 4 hydrogens and 2 here, what can I do to fix that? Any ideas? Multiply by 2, so let's try to do that. Red. So let's try if this works. So now I have a 2 there. And let's try to wrap things up with the oxygen and see if we can make it. So now I have how many oxygens in the reactants? Oxygen is only here, right? So I have 2. And in the products, I have how many? 4. I have these 2, and then I have 2 times 2, so it's 4. So 2 oxygens here. Do we all see 4 oxygens? So this is 2 oxygens plus 2 oxygens, right? Because it's here, and we multiply this by 2. So I have a total of 4 oxygens in the products. So how do I fix it? How do I fix it? I think we're all tired brains. Maybe we should take a little mini break and come back to freshen up. I put a 2 here. Everybody agrees? Yes? Okay. So I'm calling this. Let's take a 2-minute break so we can come back and refresh. Just a 2-minute break. Or maybe just get up, walk around your desk. It's good to move around, right? You should be moving every hour. And you know what's always great to oxygenate the brain? Exercise. I used to do this when I was teaching high school. I had the students get up and do 10 jumping jacks. And I'm not kidding you. Yeah. We are, well, it's, yeah, we're at 100, we're at 80, and we have 110, I think. I'll pick and choose some good stoichiometry problems. And I think Well, it's kind of thermodynamics. We might have to do a few. I'm not sure that I'll be able to be here next Friday, but whoever will be. Right, right. Thermodynamics, and then there is the whole orbitals business, and then gases. I think so far everybody told me that they have the. There you go. I'm going to mark the ones that I want to do because we have about 20 minutes, so I'm trying to do one of each or something. So this is like one easy one with just moles, right? And then something a little more complex with grams. Yeah. So we're doing this, which is simple. This is kind of like the same, so we don't need it. Right. So we can do this.
What's that? That's my own YouTube channel. I send most of the stuff I do and whoever I'll check with them. Then if they're send it to them, if it's up to you, send it to all the other. Yeah, the other ones.
One with grams. Yeah, I want to do grams plus grams limiting reactants. I'm looking for one of those. Yeah, right. This gives you everything. PB, PBO, SO2. So.
Then we are almost there.
Yes, and so we're doing 96. So at the minimum, we'll do these 3, and then what else is there? Forgot about these. Net-ionic equations. He didn't put any. Redox. Well, we'll see if we get to some of this. Yeah. The rest is, I mean, this is the. Plus, I can't even remember if there is much in the final. Yeah. Okay, so we are doing this. Okay, so you look at the equation there. Yeah. Yeah. Okay.
We'll continue until the pizza is done. Then we'll have all the stuff there. So next week I will come and show them to have a review of my students. And whoever will come, let's continue with the project.
I think it's Vivian and.
can assure her she used me. She came on time, so that's now laptop. Sometimes I work from home.
Oh, I see.
Here. Yeah.
So which tool is this?
Ink to go. Ink to go. INK 2, number 2.
Yeah.
That's
I think I have it on my PC too. Yeah.
And it has a camera on and then recording. It's recording now.
Maybe I should stop the recording now.
What experiments is very cumbersome.
Well, yeah, because it's only one file now, right?
Yeah.
We stop it, it's going to have to be 2. Okay, folks, that's gentleman in there, I think, left, but doesn't look like he's coming back. So let's start over. I think everybody's here. Okay, so we're going to do, I picked 3 good questions of stoichiometry in increasing difficulty. So we're going to start with this one, which is easier. So stoichiometry is about, once you have a balanced chemical equation, you want to figure out a way to predict how much products you're forming, or you might want to ask the question how much of this second reactant you need to react stoichiometrically with a given amount of the first reactant. So let's see, in this case, it's asking how many moles of iron are necessary to react completely with 1.75 moles of oxygen gas. And they give us the balanced chemical equation. Now, 99.9% of the times you will have a balanced equation given to you, but it doesn't hurt to check, right? So give a quick swipe. if you don't see coefficients, give a quick swipe to the equation to make sure it is balanced. Now, once you have a balanced equation, what do these numbers mean? This 3, this 4, and this 2. It means that you need 3 moles of oxygen gas to react with 4 moles of solid allylic iron, and that will yield 2 moles of iron 3 oxide, right? No, iron, what is that? FeO3. Is there something missing in here? This looks like there should be a missing too. Do you know of that compound existing, FeO3? Yeah, it's got to be a typo, right? It has to be a 2 here. But we don't care. We're just doing the math here. So, and this proves that even, because these are taken from the ACS study guide, so even the ACS study guide can have typos. I don't know that compound existing. Okay, so we have 1.875 moles of oxygen gas. So this is given, 1.75 moles. And what do we want to know? How many moles of iron? So how do we use the balanced chemical equation to do this conversion? Now, sometimes numbers could be easy. Sometimes numbers can be a little more complex. Now, if in any situation, if the numbers are too complex and you can't do it in your head, you can't see the proportions in your head, you create a conversion factor using the coefficients of the balanced chemical equation. So what this tells us is that for any 3 moles of O2, you are going to need, so we created this kind of equality, this fake equality, 4 moles of solid iron. And you convert that into a conversion factor. So I have given 1.75 moles of O2. How do I set up my conversion factor to convert those moles into moles of iron? What do I put on top and what do I put at the bottom? I need to eliminate mole of oxygen as a unit and get moles of iron. So what do I put at the bottom? So at the bottom goes oxygen, so 3 moles of O2 gas. And on top, it's going to be 4 moles of solid iron. Can somebody tell me what that yields? divided by 3 times 4 should be 2 something. And there's really only one option for 2 something. 5 is way too much. And this is the same, and it's not a 1-to-1 ratio, and this is lower. So this goes away, and this goes away. I don't even need to do the math, right? Do you all see why and how I could eliminate the other options? So 0.75 would correspond to a 1-to-1 ratio, which is not, right? So this is supposed to end up being a little more 1.75. So clearly it can be 1.31, and 5.25 is way more. It's like 3 times that 1.75. So the only option I'm left with is C, 2.33, which hopefully is our right answer. Everybody sees it? Okay, good. So now, this was somewhat easy. Let's go to something a little more complex. So these are the easiest type of stoichiometry problems, mole to mole, right? It just makes you relate moles and moles. So you really only have one conversion factor that you get from the coefficients of the balanced chemical equation. Now, let's see something a little more challenging. I think I have picked this one. A little more challenging. So what is the theoretical yield of aluminum chloride? Aluminum chloride is this guy right here. That could be obtained from 6 moles of barium chloride and excess aluminum sulfate. Now, if it says excess, what does that mean? It means that the aluminum sulfate is not the limiting reactant, right? Anybody remembers what the limiting reactant is? Is the one that runs out first, is the one that determines how much product you can get. So what this tells us is that we have tons of aluminum sulfate. So this is excess. And this is going to be limiting, which means we're going to do all of our calculations using the amount of barium chloride given, and we don't worry at all about the aluminum sulfate because that means we have enough of that. So they're kind enough to give us all the molar masses, but we start from barium chloride, which is given in moles. So in here, this problem will be going from moles of barium chloride and using the coefficients of the balanced chemical equation, we are going to go from moles of barium chloride to what? What is the only thing we can determine from the balanced chemical equation? The moles of aluminum chloride, right? So the balanced chemical equation allows us to go from moles of one to the moles of the other. And then once we have moles of aluminum chloride, how am I going to get to the theoretical yield in grams? You know this. Remember, don't worry about copying everything down because you have these slides, right? Just write down what you need. So moles of barium chloride to moles of aluminum chloride, and then eventually we're going to get to grams of aluminum chloride. So what conversion factors are we going to use for each one of these conversions? Now, to go from moles of barium chloride to moles of aluminum chloride, I have this 3-to-2 ratio, right? So the balanced chemical equation tells us that each 3 moles of barium chloride will yield 2 moles of aluminum chloride. This is moles. This really takes some getting used to. And then what is the second conversion factor I'm going to need here? Aluminum chloride moles to aluminum chloride grams. What am I going to need? How do I convert moles to grams? Moles to grams. We are completely burned out. We're gone. You know this. Yes. So we're going to need this, right? And so we know that 1 mole of aluminum chloride equals 133.3 grams of aluminum chloride. So I am going to set up my calculations starting from what they give me, which is the 6 moles of barium chloride. So I have 6 moles of barium chloride. I'm going to use my first conversion factor, is this 3 moles of barium chloride to 2 moles of aluminum chloride. What do I put on top? What do I put at the bottom? Top is where I'm going, right? Bottom is what I want to eliminate. So I'll put 2 moles of aluminum chloride over 3 moles of barium chloride. And remember, if you put all the units and you put down what everything is, you literally cannot go wrong, because you're going to see if something is messed up, because you can't cancel it out. And then lastly, we're converting, so this cancels this out, right? And then lastly, we have to convert moles of aluminum chloride into grams using its molar mass. So 133.3 grams of aluminum chloride for each 1 mole of aluminum chloride. And if we are lucky, that should give us our answer. Let me know what you get. I'll do it as well. So 6. What did you get? 533 point something. So it should be C, right? Okay. Wait, how do I, this? So why am I writing on the thing and it's not the, how do I change it? Did I forget how to change it? Yeah, I go to the, how do I go to the arrow so I can move it around? But it's not clicking, it's not doing it. No. Yeah, no, it's just writing, and I can't, yeah, I can't, it just froze. Yeah, see, I click on it and it doesn't do, it doesn't give me the arrow anymore. It just writes. There are likely something I'm doing wrong. But... This one? This one or this one? The blue one? Yeah, it's just writing on it, basically. Yeah, see, it's still a pen. Like it's... Yeah, it seems like it won't let me change anymore. Even the computer said enough of this.
Yeah, well.
I messed it up.
Yeah, that's fine. We can stop it, so it's not going to stop. It's stuck on the on this. Yeah, well. So even the recording is not I hope it's not, we lost the whole recording. I hope not, so let's see.
Sorry guys, technical difficulties.
Yeah. Well,
Even the PC is tired. He said, go have pizza. No, it's not like it's working. I thought it was me, but I guess it's not.
no, it's not. Now it's, I think, switching now. Yes.
No, oh, okay. Huh.
Yeah, it's stuck for some reasons. You can just
Yeah.
swipe after that.
Okay, guys. So if you want to stick with me, I have one more for you, which is going to be a little more challenging. Which one did I pick? Number 6. Okay, so let's pick this one, which is kind of like the whole 9 yards. Okay, so this is about as complex as it gets when it comes to stoichiometry problems. So we're given a reaction for the production of lead. What is the theoretical yield of lead that can be obtained by the reaction of 56.33 grams of PbO and 33.80 grams of PbS? So there is a more brainless way of doing this. Just do the calculations and you see what you get. And there is a more, we have to think about it, ways of doing this. Now, what we do know from this equation is that we need 2 moles of PbO for each 1 mole of PbS, right? So we need a 2-to-1 ratio in moles. And they give us grams of both. So what is the first thing to do? I can hear you. You forgot. Okay. Then let's do it together. So first thing to do, and as I said, there are 2 ways of doing this. One approach is, if you don't want to think about much of it, you just take the 2 given amounts in grams of the 2 reactants, and you go all the way, you calculate how much of the product you can get with each of the 2 starting materials. And then you look at which one gives you the least amount of product. That is what happens, basically. That is your theoretical yield, and the reactant that gave you that smallest amount of product is your limiting reactant. So that's the more, I guess, brainless way of doing it. So we can start by doing that, and then if you want to stick around, I'll show you the quicker way, but more you'd have to think about it. So we have these 2 amounts in grams. Let's set it up so that we can calculate, all the calculations. So let's start with 57.33 grams of PbO. And then let's start our setup. We are going to need 3 conversion factors here because we're going from grams to grams. The first and the last conversion factors are going to be respectively grams to mole and mole to grams, and the middle one is going to be the mole to mole one, the one that we get from the balanced chemical equation. So what is the molar mass of PbO? They give it to us is 23.2, right? So what is the first conversion factor? How do I go from grams of PbO to moles of PbO? 1 over, right? So 1 mole. And if all the units don't stick, I'll try to do my best. But so PbO is 223.2 grams. And this is PbO. Then the middle one, and we are trying to produce lead. So we are going from here to here. So it's a 2 PbO to 3 Pb, right? That's the mole-to-mole ratio. This is PbO. So I have 3 moles of Pb formed for each 2 moles of PbO. So what is that middle conversion factor? 3. Well, let's think about it. What do I want? What do I want to get? I want to get to the PB, right? So the 3 goes on top because that's what I'm going. So 3 moles of PB for each 2 moles of PbO. And once everything is canceled out, so these moles of PbO cancel with these moles of PbO, and these grams of PbO cancel with these grams of PbO. So after I've done these calculations, I am left with moles of Pb. So now next will be to convert this to grams of lead. So I'm multiplying by the molar mass of lead, right? So 207.2 grams of lead for each 1 mole of lead. So this is my first setup. And then I will do exactly the same identical setup, starting now from the PbS grams. So this 33.8. So 33.80 grams of PbS. And let's set up our 3 conversion factors. So the first conversion factor will be what? Yes, ma'am. So 1 mole of PbS divided by 239.3 grams of PbS. And what's the middle? So now we are going from PbS to Pb, right? We are doing this. So it's a 1 to 3. The top is still lead. So the top doesn't change. It's still 3 moles of lead. But the bottom needs to cancel out with the moles of lead sulfide. So 3 moles of lead for each 1 mole of lead to sulfide. Jeez. And last, what's the last one? Yes, ma'am. So let's see what you come up with, and then we'll decide. Yeah. So this comes out as 79.83 according to my calculations. 83 grams of Pb. And the bottom one, it's 87.80. So sure enough, both of these numbers are in there, right? As possible answers. So which one do we pick? Why? So if I pick 87.80, that's the highest of the 2, right? Am I going to have enough of the other reactant? No. So you pick when you do it with this method, you pick the lowest one. This can't even happen because you don't have enough of the other reactant. So the one that you get the biggest one amount, you completely ignore. You've done it for nothing. That's just to make you be able to allow you to decide between the 2. This is what happens. So this is the more like what I like to call the brainless way of doing it, because it's more calculations, but you know, you get 2 numbers, you pick the lowest one, and that's it. And well, so if you go from grams to grams, and let's make it clear, it's grams to grams here we're dealing with. So you're getting the smallest amount of products. That's the limiting reactant, and that's what happens. You're picking the lowest one when you're comparing amount of products formed. Because then I have students picking the lowest amount of moles of reactants, which could be very misleading, and it would be the wrong thing to do, because that depends on what this ratio is. You need 2 moles of these for each one of these. So if you go all the way to amount of products, and either you have grams or moles of products, you pick the small ones, the smaller one of the two, and that is going to be the amount of product that forms. And the reactant that created that is your limiting reactant. So this PBO is limiting. You're not getting the same numbers? So 57.33. You got it? Okay. Yeah, sometimes all it takes is flipping a number. And I have a dyslexia with numbers, and I'm guilty of that multiple times over. I do that a lot in my calculations, so I know that problem. So the other option for solving this question, which would likely be quicker, is to convert both of these two amounts in grams, the two reactants in grams, in moles, and then see how those moles ratio compares to this 2-to-1 ratio. That, though, requires you to be a little more, on top of it. So I would come on in here, show your face too. But that is the answer. So C is the answer. Yes, I think we should probably. Oxidation. Okay, let's see. Okay. Oh goodness, this got stuck again. Okay, let's see. Oh no, it's fine now. So what you need to do is go to a different presentation, and it. Okay, let's see. Fraction of lead. Same one. Huh. Carbon reduced. Well, want to do this one? Yeah. Okay. Oh shoot, I'm not supposed to do that, am I? I forgot. Yes. Okay. 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 So super quickly before we wrap this up, in which reaction is carbon reduced? How do we figure out reduction versus oxidation? What is reduction? What is oxidation? And how do we figure? So what do we need to look at to figure out if something is reduced and oxidized? And these are full redox reactions, so you don't have the half reactions that you see where the electrons are taken or given away. So what is the only way to figure this out? Looking at the oxidation states. Do we remember the word oxidation state? Yes, no, maybe. I don't think so. I haven't seen that one. Well, the oxidation state is kind of like, I don't know, you can think of it as like a fake charge, sort of. And sometimes it is the charge. So just to review, the oxidation state of an element, when it hasn't lost any electron or gained any electron, is 0. So if you have just metallic lead, like we had in the previous reaction, the oxidation state of that would be 0. But if now lead is in a compound, like we had, PBO, right? Then the oxidation state of this lead is not 0 anymore because it's in a compound. And you know that when you put elements in compounds, they lose their electrons, or at least they share them. So what is the charge of oxygen? Almost always. What kind of ions does oxygen do? Where is oxygen in the periodic table? Which group? 6, which means that all elements make ions because their biggest desire is to become like a noble gas. So oxygen being in group 6, his only option is to become like neon. If he wants to become like neon, how many electrons does he need? 2. So if oxygen is -2, what does lead have to be? +2, right? So that is the charge of lead in this ionic compound, and it's also the oxidation state. So basically, we need to figure out the oxidation state of carbon before and after this in the reactor and the products, and how do we decide if it's reduced? What is reduction and what is oxidation? Remember oil rig? That may be oil rig. Oxidation is loss of electrons. Reduction is gain of electrons. So oxidation is loss of electrons, and reduction is gain of electrons. So in our example of lead, we said lead by itself is 0, but lead in this compound is +2. If I go from lead +2 to lead 0, how do I go from a +2 charge to a 0 charge? How many negative charges do I need? 2. So in going from lead +2 to lead 0, I basically need to gain 2 electrons. So that would be an example of a reduction. If I do the opposite reaction, that would be the oxidation. I'm losing electrons. So by comparing the oxidation states and seeing how many negative charges do I need to go from the oxidation state of the carbon, in this case, in the reactants, to the oxidation state that carbon has in the products, I can decide in which one of these reactions carbon is reduced. So we're looking for a decrease in the oxidation state, kind of like we did in here, from +2 to 0, that would be the reduction, gaining electrons. So let's calculate what the oxidation state of carbon is for all of these reactions. Now, for pretty much all of these, we can use the following rules. Hydrogen in compounds is +1. Oxygen in compounds is -2. So let's see. We are going to figure out the charge of, or the oxidation state of carbon in all of these, looking at these rules. What is the oxidation state of carbon here? It's paired up with one oxygen, which is -2. What would be the oxidation state? Remember, the sum of the oxidation states is to be equal to 0 because that's a neutral compound, right? So if oxygen is -2, what is carbon? +2. Now, if oxygen is -2, what is carbon in here? If oxygen is -2, we have 2 oxygens, so the total negative charge here is what? We're fried. Brains are not working anymore. So if this is -2 times 2, that's -4, carbon has to be +4, right? So in here, we are going from +2 to +4, so it's losing even more electrons, getting more positive, right? So that's not it. Now let's look at B. CO2 is just like this CO2, so the oxidation state in here will be +4. What's the oxidation state of carbon in CO3, in carbonic acid? So let's see. This is +1, and oxygen is -2. So I have 2 hydrogens, so total positive is +2, right? Because I have 2 of them. And I have 3 of the oxygens. So -2 times 3, that's -6. What do I need to add to +2 so that the plus 2 plus something else minus 6 equals 0. Plus 4. So this reaction right here is not even a redox because carbon doesn't change its oxidation state. So we haven't found a reduction yet because this was an oxidation. Let's see what we have next. So we have still CO2, so we have plus 4. You don't have to calculate it again. And then we have CH4. So CH4 will be plus 1 on each carbon. What's the oxidation state of carbon in here? It's 1 carbon and 4 hydrogens. Each hydrogen is plus 1. So I have a total of plus 4 for the 4 hydrogens. So carbon is minus 4. Yes? So carbon here is going to be minus 4. So I'm going from minus 4 to plus 4. Does that gain any electrons? Do I add the negative charges to go from minus 4 to plus 4? No. So this is also an oxidation. And then, well, we kind of hope this is it, right? Because we have out of options here. So let's do the oxidation state of carbon in C2H2 and C2H4. And if you had some organic chemistry background, this reaction would be actually much easier because you can tell right away. So each hydrogen is plus 1, right? And I have 2 of them, so it's plus 2, which means the 2 carbons have to be minus 2. And I have 2 of them, so each carbon is what? Minus 1. And then in here, what do we have? Plus 1 for the hydrogens. And we have 4 of them, so it's plus 4, which means the 2 carbons have to account for minus 4, which means each carbon has to be minus 2. So now I'm going from minus 1 to minus 2. Is that it? Is that a reduction? Yes, right, because it's becoming more negative. So you only go from minus 1 to minus 2 if you get 1 more negative charge. So this is our reduction. Yes, sir.
There is an old designation. That's the modern designation of reduction oxidation. The old one, reaction, you heard that in the old textbooks. Reaction with oxygen is oxidation. Reaction with hydrogen is reduction. You look at all the reactions with oxygen, that's oxidation. We can't go through all this, that's correct. But the 2A and C, that's reaction pure oxygen, that's oxidation. The other one, you know, there's no change. You can see that's a combination reaction. The fourth reduction is reaction with the pure hydrogen. So within a few seconds, you have the answer. I mean, you can't go through all this, that's correct. That's what we went through, no review. But if you got the old designation of oxidation reduction, oxidation is reaction with pure oxygen, reduction with the pure hydrogen. No longer is used because that's not true. That's not always true.
But that's a very easy thing to remember, actually, because oxidation, right, reaction with oxygen, so at least you can eliminate all of them. That's what I said. If you actually knew some organic chemistry, this would be much easier to answer. But
just see the answer without
we aren't even going through all of it.
Yes, but that's not always the case. You have to do the calculations because some problems is not obvious.
Yeah, this was an easy one for somebody who knew oxidation reactions.
The V is hydrogen there, and the A and C are oxygen, so you can eliminate the oxygen. So, yeah, that's it.
Okay.
That's it. That's it.
Yes.
You want to give them another one, or that's it?
I don't know. It's 12:30 almost.
Yeah.
I think we are all burned out. So we're clicking this one.